Hello, this is section 6.1 for Calc AB, and today we'll be talking about the area of a region between two curves. So the whole idea is now you're working with two different functions, and I want the area between those two functions. And sometimes they'll set the bounds for you. Other times you'll use the intersection of the two curves, so it just depends on the problem. But the whole idea is if you find the area of your top function here, and that goes all the way to the x-axis. And then you're going to want, so here, I'll start over here. So the area from the top function all the way to the x-axis, and then we're going to want to subtract away the area under the bottom function. And that's what's happening here. So what that will leave you with then becomes the area between the two curves. So you did this in geometry when you had a big circle and there was a smaller circle inside, and we wanted the area, we called it the annulus, the area of the perimeter kind of, and you did the area of the big circle minus the area of the small. That's basically the same concept as what's going on here. Okay. Your goal is going to be to find, so whenever you're finding the area between two curves, sometimes it's not as straightforward. So you might sometimes think of it as if you were to maybe drop a marble or something, what is it going to hit first? That's going to be your first function, and what it's going to hit next, that'll be the bottom, or the second function that you'll subtract away. So you'll see what I mean when we do some examples here in a minute. And then this is just a refresher that, hey, we are still working with rectangles. We are still adding infinitely many rectangles together. It's just the height of the rectangle is now not just f of x that goes from the function to the x-axis, it's now f of x minus g of x to give a new height to that rectangle. Okay. All right, so here's what I mean about the whole dropping a marble thing. So find the area of the region bounded by the graph. So I graphed my line, my parabola. So here's my line, here's my parabola, and it specifically says from 1 to 3. So I've got to figure out what is this area here. All right, so you need to first create your definite integral, so the integral from 1 to 3, and then, so again, we're finding the antiderivative with respect to x. So what would my pencil, marble, whatever you want to think of it, what is it going to hit first as I'm dropping down from the top? And it's going to hit that line. So that's what's going to go first, x plus 3, minus, and then your bottom function here, which is negative x squared. Now, what's kind of fun about this is this right here, that integral from 1 to 3, that's going to represent negative. Remember that area we represent with a negative sign in front? And what happens is that negative and these negative values end up becoming positive, which is perfect because we want to add this area to this area. We want all this to be represented as a positive. So you do the antiderivative, use your fundamental theorem of calculus, and there ends up being the area between those two curves. All right, so not too terribly difficult, but I think determining which one goes first is important. And if you get a negative answer, that's a good indicator. You probably have these flipped. All right, and again, a more common problem involves the area of a region bounded by two intersecting graphs. So that's what the next one is. So these are our two functions. We want to find the region bounded by the graphs. So graph these. This is 3x squared minus 1, and then this one's 3 minus x squared. Okay, set them equal to each other to figure out where they intersect. This is actually one of those symmetric problems that you could put a 2 out in front and go from 0 to 1 if you want, because it looks like it's symmetrical. That's totally up to you. All right, but now here's that whole thing. You got to figure out which one goes first. So again, if you drop your pencil down, you'll notice you hit, this is actually g of x first. So it's going to be g of x minus f of x. And then you guys can do that. Plug those functions in, do the antiderivative, use the fundamental theorem of calculus, and solve. Right. Now, your calculator can also help you with this problem. It can find the intersection points. It can even find the area between the two curves. Okay, so you'll need to play around with your calculator a little bit, and we'll do that in class, of course. All right, so here's another one. Now, just keep in mind, remember we work with a restricted domain on your trigonometric functions. So technically you'd have infinitely many regions. So we're only going to work in the domain that we restrict ourselves to with sine of x. So I graphed sine of x over here and then graphed our horizontal line. So we're looking at this region right there. So set sine of x equal to 1/2 so you can solve for x. That's where I'm getting the bounds, right? Then set up your definite integral. And again, what are you going to hit first when you drop down from the top? And that's going to be the sine of x. So that's the function that goes first, minus 1/2 dx. All right, next one. Sketch the region bounded by the graphs and find the area of the region. All right, so here's where it just gets a little more complicated. So we graph to the functions, okay? And we notice immediately that, hey, we have two regions that we're working with. When that happens, you will have to break it up into two separate integrals. So that's what I've done here. Now this first one goes from 0 to 1. And if you notice, as you drop your pencil down, it's actually f of x that you hit first. So it's f of x minus g of x from 0 to 1 dx. Plus, and then the integral from 1 to 5, again, as you drop your pencil down, it's actually g of x that you hit first this time, and then f of x. That's why those flip there. So you kind of really needed the visual to help you see that. Okay, now we can also find these regions in terms of y. So what we just did when we were finding the integral in terms of x, we did top minus bottom. So we dropped down top minus bottom. If it's more convenient to find the area of the regions in terms of y, which sometimes it is, you're going to want to go from right to left. Right, so you'll use your pencil right to left. You could also turn your paper and then it becomes top bottom again, but you just have to think of it from right to left. All of the problems that we just did, well, let me come back up here. These three first problems that we did, notice that the top and the bottom were consistent, the entire region. Top and bottom were consistent, top and bottom were consistent. Now with this one, the top and bottom, we had it changed, so we had to break it up into two separate integrals, right? And even if we went from right to left, that's not going to work either here. So, but in this next example, we went ahead and graphed. This can be solved both ways. You can go top to bottom, or you can go right to left. And it's already in terms of y, so you can see how it's convenient to go ahead and keep it, go from right to left. Now, coming back up here, if we were to do right to left with this one, you'd have to break it up into two separate integrals. Okay, so it still wouldn't really work there. So you just have to kind of evaluate your situation and see if you want to use top and bottom or right and left. It's up to you. It'll still work either way. Okay, so what I did is, again, you have to figure out the intersection points. But now when you go to set up your integral, we're going from right to left, you're going to use the y values for your bounds. So your lower y value is -4, that's your lower bound, and your upper bound is -1. And then if you're going from right to left, the line is what you hit first. As you're moving your pencil from right to left, that's what you hit first. So that's your first function minus the left function, dy. Now, if you were going from top to bottom, notice I switched the bounds. So now I'm using the x values, that's the lower bound and the upper bound. And in this case, if we're going this way, now I had to solve both of these to get them in terms of x. That's what's over here. All right. So in this case, it's going to be your line, but solved for in terms of x minus the square root. Now the square root part, you have a plus or minus here. The top is your positive. You're down here with the negative square root, so that's why it's the negative part there. But I think it's arguably easier to get it to keep it in terms of y, but you get the same answer either way. Okay, now this last part, this is actually a build-up to what's going to be in the next section. So it's just, again, refreshing your memory on the fact that you are dealing with rectangles. The area formula in this section was developed as followed. So you're still building off of the area of the rectangle as your base. So again, this is a build up to the next section, right? And then here's one other, just a quick little lesson closer, and setting up the integrals. This is just a good little practice problem that you can read through. So just please make sure you do your homework. Make sure you're practicing on your graphing calculator, because getting the visuals for these is really important to seeing what the top and bottom is, seeing if you should do the area in terms of X or in terms of Y. If you're in terms of X, it's top minus bottom, but if you're in terms of Y, it's going to be right minus left. And you'll need to make sure the bounds are in terms of Y. And so you just need to practice. It's not terribly difficult, but you've got to make sure you're doing your homework. So, okay, email me if you have any questions.